So we've got the function f of x is equal to x squared. And what I'm concerned with is finding the area under the curve y is equal to f of x. So that's my y-axis. This is my x-axis. Then let me draw my function. My function looks like this in the first quadrant. That's where I'll graph it for now. I could also graph it obviously in the second quadrant. But what I care about is the area under this curve and above the positive x-axis between x equals 1 and x equals 4. X equals 4. And I'm tired of approximating areas. I want to find the exact area under this curve above the x-axis. And the way we denote the exact area under the curve, this little brown shaded area, is using the definite integral. The definite integral from 1 to 4 of f of x dx. And the way I conceptualize where this notation comes from is we imagine an infinite number of infinitely thin rectangles that we sum up to find this area. And let me draw one of those infinitely thin rectangles, maybe not so infinitely thin. So let me draw it like this. So that would be one of the rectangles, that would be another rectangle. This should be reminiscent of a Riemann sum. In fact, that's where the Riemann integral comes from, taking a Riemann sum where you have an infinite number of these rectangles, where the width of each of the rectangles, this is how I conceptualize it, is dx, and the height of this rectangle is the function evaluated at an x that's within this interval right over here. And so this part right over here is the area of one of those rectangles, and we're summing them all up, and this is kind of an elongated S reminiscent of a sigma for summing. We're summing up the infinite number of those infinitely thin rectangles, or the areas of those infinitely thin rectangles between 1 and 4. So that's where the notation of the definite integral comes from. But we still haven't done anything. We've just written some notation that says the exact area of between 1 and 4 under the curve f of x and above the x-axis. In order to actually do anything really productive with this, we have to turn to the second fundamental theorem of calculus, sometimes called part 2 of the fundamental theorem of calculus, which tells us that if f has an antiderivative, so if we have the antiderivative of f, so f of x is derivative of some function capital f of x, or another way of saying it is capital F of x is the antiderivative of lowercase f of x, then I can evaluate this thing, and we do a whole video on conceptually understanding why this makes sense. We can evaluate this by evaluating the